galvanic cells. So question 8 is always about the voltaic in galvanic cells. And then question 9, what happened to the rest of this paper? There we go. Question 9, let me just turn that around. Question 9 is about electrolytic cells. Okay, so there is another, if you pick up other papers, you will see that there's a question 10, and question 10 is about fertilizers, and fertilizers has been removed from the syllabus. After that, they'll give you a periodic table, and they'll give you the redox tables, as well as, I see they didn't include it here, as well as a list of chemical formula that you're going to use. Right, so the other document that you got is 2019 Physical Sciences. Again, you'll notice question 5 is rates of reactions. Question 6 is chemical equilibrium, and question 7 over there is again acids and bases. And then we gave you another document. Again, you'll notice again, question 5 is rates of reactions, question 6 is chemical equilibrium, and question 7 is acids and bases. Right, so the program for the day is I've divided the day up into 3 sessions. We know the 3 sessions. The 3 sessions are starting right now until 10:45, on which you will get 15 minutes break. If we finish all 3 questions a little bit earlier, you can go to break a little bit earlier, but that is highly unlikely. And then, so for the first session, we will be concentrating on acids and bases. Okay, so it's a 2-hour session. Acids and bases is a tough session, a tough section. So what I've done is I've used the 2-hour session for the acids and bases questions, and then after that, in the second session, we will do rates of reactions, and in the last session, we will do chemical equilibrium. So what I've done is I've separated the questions, and the questions is in that order. The first, just to remind you, that your first question says Physical Sciences Chemistry Paper 2, 2019, and then we gave you another Physical Sciences Paper 2, 2019, which was the backup paper, and then we gave you February, March 2018, which is the third paper. So the questions are as is in the document from the first paper, which was complete, and the second question will be from the second 2019 paper, and the third question will be from February 2018. Right, so without further ado, what I'm going to do is I'm going to work very slowly with you through the first question. I'm just going to share this document with you. Jane, how do I get rid of this? How do I get rid of this? Okay. Right. So, we'll start on our first. We will start on our first question relating to acids and bases. Now, the balance equation below represents the first step of ionization of sulfuric acid in water. Right, so if we look at this ionization over here, this shows the first step of ionization of sulfuric acid in water. And I just remind you of our Lowry-Bronsted definition of acids and bases. Our Lowry-Bronsted definition of acids and bases says that an acid is a proton donor. And when we refer to, just to show you, so Lowry-Bronsted says an acid is a proton donor. Now, why am I not? Why is this not on there? Okay, hier server struck me. Okay, so I'm looking like I have a technical problem here. Let me just double check. I'm mirroring. Well, there we go. I'm back. Right, so as I said before, we're looking at the ionization. We're looking at the ionization of an acid, and we said that our Lowry-Bronsted definition is that an acid is a proton donor. So what do we mean by a proton? Right? So hydrogen is atomic number 1, and on the periodic table, you'll notice atomic number 1 means 1 proton. So hydrogen has 1 proton and it has 1 electron. So hydrogen has 1 electron and 1 proton. So when hydrogen loses the electron, what is left over is the proton, which is positive. So when we refer to an acid is a proton donor, we are referring to an H plus ion. Okay? So a proton is an H plus ion. So when we now say, and we look, write the formula of 2 bases. Okay, so we know that an acid is a proton donor, a base is a proton acceptor. So let's have a look. We've got H2SO4 reacting with water, and what actually happens is that the H2SO4 donates an H plus to the water, and we get H3O plus HSO4 minus. So what has happened? What has happened is that the H2SO4 donated the proton, so it has acted as a proton donor, and the H2O has accepted a proton, so it has acted as a proton acceptor, which means that the H2O acted as a base, and the H2SO4 acted as an acid. In the reverse reaction, remember this is a reversible reaction. If we look very carefully, in the reverse reaction, the proton goes the other way. So the H3O plus donates a proton to the HSO4. So the H3O plus, when it donates a proton to the SO4, becomes H2O. And the HSO4, when it accepts the proton, becomes H2SO4. So, in the reverse reaction, the H3O plus acted as an acid, and the HSO4 acted as a base. So the question being, and I read, write down the formula of two bases in the equation above quite clearly. That is the base, and the water is the base. So, our answer there very clearly is H2O and HSO4 minus. Right, just a little bit more about acids and bases. If we look carefully, at what I've written, this thing is dropping me today, I don't know why. It never drops me. Come on. Alright, I'm back. Alright, so when we spoke about an acid being a proton donor and a base being a proton acceptor, you just have to be a little bit patient with me. The technology is dropping me this morning. I don't know, it never drops me. So when I look at an acid being a proton donor and a base being a proton acceptor, I just need to remind you that the H2SO4 over here and the HSO4 minus is what we call a conjugate acid-base pair. Dropped me again. And the water plus the H3O plus, and the water plus the H3O plus is my other conjugate acid-base pair. So those are conjugate acid-base pairs. Notice the substance formed when an acid donates a proton is called a conjugate base, and the substance formed when a base accepts a proton is called a conjugate acid. Okay. Is sulfuric acid a strong or a weak acid? Is sulfuric acid a strong or a weak acid? Right. Give a reason for your answer. Is sulfuric acid a strong or a weak acid? So this is the ionization of the acid. So there we have the ionization of the acid. So what I want you to notice is on the left-hand side of the equation, we have molecules. So we have molecules of sulfuric acid and molecules of water. On the left-hand side of the equation, we have molecules. Molecules of sulfuric acid and molecules of water. On the right-hand side of the equation, we have ions. So when we speak about ionization, we speak about the amount of acid molecules and water molecules that became hydronium ions and hydrogen sulfate ions. So in the case of a strong acid, all the molecules becomes ions. Drop me again. I hate this.
Graham, what if you use the document camera rather?
Yeah, I'm thinking of using the document camera.
You can grab you some of the paper.
I've got that. Flame. And I've got pens. Right, so we're going to plan B, because my iPad keeps on, the system keeps on dropping me. So what I'll do is I'll switch to the document camera. I'll just open up this document over here quickly. Just be patient, I am switching my plans. Right, so. Right, so what we had was that we had okay, I'm going to do it this way so it's better. Okay, H2SO4 plus H2O goes to H3O plus HSO4 minus, HSO3 minus. Right. So that is the ionization. What I was trying to say earlier on is that on the left-hand side, I only have molecules, and on the right-hand side, I have ions. So the definition of a strong acid is an acid that ionizes completely. What that means is that all the molecules became ions. Okay? And that is why it's referred to as the ionization of an acid in water. Okay, so when they ask you, and just to remind you what they asked you, because you have it in front of you as well, but just to remind you what they asked you, that's not the question. That is the question we're busy doing. They asked you, so we wrote down the formula of two acids, of the two bases, and the next question was, is sulfuric acid a strong or weak acid? Give a reason for your answer. So a strong acid ionizes completely, and a weak acid ionizes partially. So if I give a reason for the answer, is sulfuric acid strong or weak? We will say that sulfuric acid is a strong acid because it ionizes completely in water. Okay? Sulfuric acid is a strong acid because it ionizes completely in water. Alright, do you have a Cokie?
No, but I think I get.
Yeah, I'll get a Cokie. Okay, so we're going to get a Cokie so that I can write something that is thicker, because our technology dropped us, so we're going to plan B. So if you're patient with me, when I get a Cokie, I will switch over to a Cokie. Right, so the next thing we're going to look at is the question. Right, and I read, learners use the reaction of a 0.15 mole per decimeter cube sulfuric acid solution with sodium hydroxide solution in two different experiments. That's the balanced chemical equation for the experiment. They use 24 centimeters cubed of sulfuric acid in a titration to neutralize 21 centimeters cubed of sodium hydroxide. Calculate the concentration of the sodium hydroxide. Right, so what we have, and I'll switch over to the document camera again. What we have is we have sulfuric acid reacting with sodium hydroxide, and we're getting sodium sulfate plus water. Right, and if we balance the chemical equation, we put the 2 over there and the 2 over there, and we have a balanced equation. Right, so the most important thing here is that I prefer learners not to use the equation CAVA over A. I want it to be a mole calculation, because most of the other calculations are mole calculations, and if they use that equation, they continue using the same equation for anything else. Right, so I remind you, and look, they use 24 centimeters cubed of sulfuric acid to neutralize 26 centimeters cubed of sodium hydroxide. And the concentration of the sulfuric acid is 0,15. Right, so moles of sulfuric acid is equal to concentration times volume, and the concentration is 0,15, and the volume is 24 centimeters cubed, which is 0,024. And if we plug that into a calculator, we get 0.15 multiplied by 0,024, and we get 0,0036 moles. Right, so now I have the moles of sulfuric acid, and what I look at is the mole ratio, and I see that the mole ratio of sodium hydroxide to sulfuric acid is 1:2. Right, which means that the moles of sodium hydroxide is equal to 0,0036 multiplied by 2, which is 0,0072 moles. Right, so, and then concentration is moles over volume, and we get 0,0072 divided by, and the volume of sodium hydroxide was 0,26 divided by 0,026. And notice, I remind you that there is 1,000 centimeters cubed is equivalent to 1 decimeter cubed. 1,000 centimeters cubed is equivalent to 1 decimeter cubed. And I found a Koki, so I will write with the Koki henceforth. But doing the calculation, 0,0072 divided by 0.026, and we get 0,28. Moles per decimeter cubed. Right. So, it is a mole calculation. I remind you, when I read this equation, I read it as 1 mole of H2SO4 reacts with 2 moles of sulfuric acid to produce 1 mole of sodium sulfate plus 2 moles of water. What we want to do, if I want to find any moles, I need to know the number of moles of one of these reactants or products, and I can work my way to any other one. So, given the information, I could calculate the moles of sulfuric acid, and then I could work my way to the number of moles of sodium hydroxide, and then calculate the concentration. Right, so the next question in another experiment, 30 centimeters cubed of sulfuric acid is added to 20 centimeters cubed of a 0,28 mole per decimeter cubed sodium hydroxide solution in the beaker. Calculate the pH of the final solution. Now this is a classic question. This question pops up over and over and over again. And for all those learners and teachers that was with me on the program that we do during the week on a Thursday afternoon, I did quite a few of these. So, in this case, and this is the reason why I insist that people use the mole calculations. Okay, so again, we have the equation H2SO4, and I'm just going to show you the document camera again. We have the equation H2SO4 plus NaOH goes to Na2SO4 plus water. Plus water. Right, so what they've done is they've given us 30 centimeters cubed of sulfuric acid. So I'm going to write my 30 centimeters cubed over there. And they've given us 20 centimeters cubed of sodium hydroxide. So it's the same sulfuric acid. It's the same sulfuric acid. So the concentration is 0.15 moles per decimeter cubed. And the concentration of the sodium hydroxide is 0.28 moles per decimeter cubed. Which means, now let me just make you a little drawing, just to give you an idea of where we are going. So we have the acid, and we have the base. And what we are doing is that we are mixing the acid and the base, so they're both going into one container. And I call that the mix. And in the mix, the reaction happens. In the mix, the reaction happens. And when that reaction happens, when an acid reacts with a base, it neutralizes. So some of the acid and some of the base is going to be neutralized. However, one of it is going to be in excess. One of it is going to be in excess. So the acid will have a particular volume, let's call it V1. The base will have a particular volume, let's call it V2. But if I put both of them in there, then the total volume is V1 plus V2. Right. Then the other thing that we spoke about before is that one of them will be in excess. Okay? One of them will be in excess. So one of them will have a total number of moles. So I always use this little equation. Total moles is equal to reacted moles plus excess moles. Right, so the total moles is going to be the reacted moles plus the excess moles. Right, so we need to first determine which is the limiting reagent, right, so that we can determine how much leftover moles there are. So before we can do that, we have to balance the equation, and if I put a 2 there and a 2 there, then we have a balanced equation. So I'm going to start off by calculating the moles of sulfuric acid, and that is equal to concentration times volume. And that gives me, the concentration is 0.15 multiplied by 0.030. Okay? And that gives me 0, and I'll put it into the calculator, and you can put it into your calculator in the meantime. 0.15 multiplied by 0.030, and I get 0,0045 moles. Right. And now I'm going to look at the moles of sodium hydroxide. So the moles of sodium hydroxide is concentration times volume. And I get 0,28 multiplied by 0,020. And I get, if I multiply those two, I get 0,0056 moles. I did that mentally, so let me just double check on my calculator. 0.0056 multiplied by 0.020 equals, and no 0.28, sorry, multiplied by 0.020, and yeah, 0.0056. So now we've got the moles of sulfuric acid and we've got the moles of the sodium hydroxide. And we notice that they react in a ratio of 1:2. They react in a ratio of 1:2. So in other words, if they were going to completely neutralize each other, the sodium hydroxide must be double the amount to the sulfuric acid. But if we look at the numbers that we've got, we don't have that numbers, which means we can assume that sodium hydroxide is the limiting reagent. Okay? So in other words, the moles of H2SO4 that reacted is going to be 0,0056. And why am I using the 0,0056? Because all the sodium hydroxide is going to be used up. It is the limiting reagent times a half, because the ratio, I use double the amount of sulfuric acid, which means I'm going to use half the amount of H2SO4, which gives us 0,0028 moles. Right, so let's just go back to our little drawing and our little equation. Okay, I have the total moles of sulfuric acid, which is that. I have the reacted moles of sulfuric acid, which is that. And in our little equation, I can now work out the excess moles of sulfuric acid. Right? So the moles of sulfuric acid in excess is 0,0045 minus